Hello and welcome. I'm Tom Palmer. Tonight we're speaking about cognitive neuroscience. With me is Dr. Mark D'Esposito, Director of the D'Esposito Cognitive Neuroscience Laboratory at the University of California at Berkeley. Welcome.
Thank you.
Thanks for coming.
You're welcome.
Well, I've been reading a lot about the topic. It just seems like one of the most interesting fields in science right now. People are so excited about being able to monitor the brain in ways that they never could before. Your lab seems focused on the frontal cortex.
Right. I think a lot of what's driving all the excitement is that we finally have the tools that can measure brain function in a way that people can understand it. And one of the tools that's been driving it is MRI scanning, magnetic resonance imaging, and this ability to sort of see the brain think has been sort of fascinating. Has been fascinating to people, and it's opened up doors into all different ways we can, look into it.
So you could correlate emotions to thought patterns?
Yeah, pretty much anything that you can ask an individual to do in real time, you can image and look at their brain activity while they're doing it. So whether it's an emotion, something emotional or something cognitive or something, unrelated to either one, it can be picked up with a brain scanner. Interesting.
And the focus of your work, you're focusing on damage in the frontal lobes?
Well, we've tried to understand the frontal lobes. I mean, if we're, the whole idea is to try and figure out how the brain works, and the frontal lobes is really what I consider kind of the final frontier of the brain. It's sort of the area that's mystified, neurologists and psychologists for many years, not really understanding what the function of the frontal lobes is. It leads to a wide range of unusual behaviors and deficits in cognitive functions that people have not really been able to pinpoint. So it's the largest area of the brain, and sort of the area of the brain we need to sort of understand to sort of understand the rest of the brain. Sort of what we know so far is that it's really sort of the top of the hierarchy of the brain. It's sort of the part of the brain that allows us to kind of orchestrate our thoughts, based on rules, intentions, goals, as opposed to being driven by, reflexive behavior and everything that's sort of out there in the world.
So is the last part to evolve?
It's the last part to evolve. It's also, interesting, the last part to develop in children. So it's the latest, the last area of the brain that develops in kids. And it actually, I shouldn't say kids because it's probably still not developed to the age 20, 25, 30. I kind of always tell a joke that, it's no surprise that insurance companies know that, have this rule that at age 20, you can't rent a car until age 25. And the frontal lobes are not really developed until sort of probably around that time, a little bit after.
Dr. Gazzaniga in his book, in a couple of his books, talks about the different spurts of growth in the brain, and that there's actually more than one. That we think of adolescence as the big time of the growth spurt, but that pubescence later, 15, 16, when all these hormonal changes are going on, that's also a second time of great neural activity in the brain.
Right. I mean, I think in terms of the frontal lobe development, there's ideas that there's actually some benefit of the frontal lobe sort of developing later, that some of the things children can do, like learn languages faster and do other things actually better than adults, sort of benefits by not having sort of a fully developed frontal lobes allows us to be more flexible and plastic and adaptive, and then we develop later after we've sort of gotten down these sort of these rules. We can sort of then we need our frontal lobes later to know when to implement them in sort of the proper context.
How does this relate to the right and left centers of the brain?
Well, that's the interesting thing about the frontal lobes. It doesn't seem to be it doesn't seem to have lateralized function like the rest of the brain. The left brain certainly is much more important for verbal language. The right seems to be much more important for spatial processing, but the frontal lobes doesn't seem to have that kind of specialization. Both frontal lobes kind of act in concert, and that's very good, because in damaged patients that we see with traumatic brain injury, we have found that if you damage, say, the left frontal lobe, your right frontal lobe can reorganize and kind of take over for it.
Plasticity.
Right.
It was the buzzword for many years. When I remember my psychology 101 course, and a long time ago in the 70s, and the established thought was that the brain is fixed. I think Darwin thought so. And
right.
So it just came from that, and everyone assumed that that was the case. And there were some pretty radical experiments
Right.
with animals that revealed that, in fact, the brain is not only plastic, but it's highly plastic.
Right. I mean, I think there's two things that we've learned that are wrong. One is that we're not born with all our neurons. There are new neurons that can grow over time. I mean, it's not in every part of the brain, but they're in certain key parts of the brain, like the hippocampus. That's important for memory. And areas that seem to be very functionally specialized for something can reorganize and develop in a new way. I mean, there's been interesting studies, for example, that patients who are blind, their visual areas, which obviously are not developed, can take on a function for somatosensory function for Braille. When they read Braille, that sort of sensory touch is actually activates what would have been a visual area in a healthy individual. So that would have never been considered possible in sort of a rigid idea about how the brain works. And so that sort of really adaptation plasticity sort of opens up all sorts of hope about how we may be able to sort of help individuals with injury and neurological disorders.
Right. Do you work at that at your lab?
We do. I'm, a neurologist by training, so most of my work has been with healthy undergraduates. But the
They make great
subjects.
You can motivate them with small amounts of money.
They're cooperative, but the whole idea is that the more we understand about the normal brain, the more we're going to learn about sort of the damaged brain. It seems counterintuitive, but actually it's true that if we can figure out the normal circuitry, then we can figure out what to do about the abnormal sort of circuitry. And so we're just starting to sort of really try and translate, and all the field of cognitive neuroscience is starting to sort of translate what they've learned in the normal brain to sort of into disorder, neurological disorders. And just to follow up, I think we're finally at a point where there is something to translate, that we can make a difference. In general, neurological disorders have been extremely difficult to rehabilitate. That it's been very hard someone who loses their memory from a stroke, it's very hard to sort of teach them ways to get their memory back. But now I think there are strategies that are starting to work.
Different techniques, and then you can measure them better than you could before.
We can measure them, and we can see what's actually, now that we see that there's other parts of the brain, reorganizing, we can, rather than trying to fix an area of the brain that's broken, we can sort of work on boosting another area that's reorganized and trying to, in a way that kind of can compensate for the impaired function.
Interesting.
Yeah.
So you also do MRIs on patients that are in a coma.
Yeah, we haven't done those type of studies, but they've been we've mostly have been done studies with patients who've had mild traumatic brain injury or stroke, and so they're fully aware of what's going on, even though they have impairments in frontal lobe function. But the scanner allows you to to image patients that are unconscious, and that's led to some really interesting work.
So what do you think the future holds for the field? It seems like it's unbounded.
Yeah, for cognitive neuroscience, I think the future of the field is that, it seems, ludicrous to think that we're going to understand how the brain works, but people who study the brain actually feel like that's something that we're going to achieve at some point.
Dr. Gazzaniga talks in terms of modules.
Right.
That you can't really understand the brain as a whole. Really, what we have is a number of modules that are themselves very complex systems. He relates any individual module as a complex system to, say, climate emerging from weather, that there's so many different variables and so many things going on that what you have is what he and others call emergence, that you have a whole nother set of functions emerging from a subset of functions.
Right. So I think this is the hottest, newest area of brain science, is that we're moving from this sort of localizationist view, which has been around for over 100 years, to a more network sort of view of the brain. And we've known for over 100 years that that there are specific areas of the brain that are very localized in their function. Dr. Broca discovered that there's an area of the brain that's just as important for producing speech, and then there's another area of the brain that's important for comprehending speech, and that led to trying to localize function in specific areas of the brain throughout. But when you think about language, how do you get the gist of a conversation? This is not, there's not an area, there's not the gist area of the brain. This type of language ability that we all have emerges from what we believe is an interaction of these modules that are highly specialized. And so we now, with brain imaging, there's actually been demonstration that modules do exist. There's not 100 modules in the brain. There's actually only about 3 or 4 modules in the brain. But it's very consistent across individuals. We seem to have 3 or 4 modules, and they all are specialized, but how they interact is really where it seems to be the key to sort of understanding them. And it's very much like a network, like a global air traffic network, and the kind of tools we use to sort of study it. There are hubs and there's connectors in the brain. There's areas of the brain that are connecting between modules, and there's areas of the brain that are very connected within a module. So like in an airport network, Barcelona would be a hub, and because it connects among all these European cities, but London would be a very important sort of is a connector between modules. And what we're kind of discovering is that how important it is to have both. You can knock out Barcelona and the world doesn't the air traffic doesn't shut down. And just like the brain, you can knock out a power module and your whole brain doesn't shut down. But if you knock out a connector like London, or the frontal lobes, which I believe is a connector, then you lead to this more sort of widespread damage to the brain. So yeah, Dr. Xander's hit the nail on the head. We have to think about the brain as sort of a network and the interactions of these modules and how function emerges from those interactions and not from these localized areas that are specific to very specific processes.
It's also an opportunity to really understand emergent systems themselves. We can't monitor the weather the way we can eventually the brain. We can't monitor, if it's true that, for example, Newtonian physics emerges from quantum physics, Dr. Gazzaniga postulates that there might be multiple levels of emergence involved there, which would make sense because you can't mathematically correlate the quantum level with the Newtonian level with the cosmic level.
Yeah, and I think getting back to the sort of the modular idea of the brain, where I said there's only 4 or 5 modules, that doesn't mean that in one module there's not a hierarchy of submodules. So it's thought that there's multiple sort of levels within each module.
Right, multiple levels of emergence within each module.
Within each module.
Right, and eventually, potentially, you can, as measurements get better, you can understand them, discover them.
Right, and this has been, and this is for the first time, with imaging, we were able to, actually discover that this exists. There was no way in the past to sort of show that there is a modular organization to the brain. So that's what's sort of exciting about the sort of where we are.
It seems that some scientists are just positively giddy about the prospects, and philosophers, and everyone is interested. People, they want to talk about free will, and they want to, it's where a lot of things sort of intersect.
Yeah, there's both sides of it. Early on with imaging, I think there was a lot of skepticism that, what does it mean to find the romantic love area and find the sort of the gist area and all these sort of things. But now that we're sort of studying it in a way that sort of can be quantified and makes sense. I mean, the modular brain, it is, as you said, it's sort of a good way to build a system. From an evolutionary perspective, it's easier to add modules to a system than to a system that has multiple than have one module. And from a neurological perspective, knowing that you can damage one and it doesn't perturb, or even when we're using one that it's not perturbing the rest of the modules, we can think about how cognition can emerge from these interactions and not just lead to this big noisy mess whenever we're thinking about something.
Do you think the question of consciousness and where it emerges from is important? Some people assume, most materialist scientists assume that consciousness emerges from the brain, and that eventually we'll be able to know how. Others postulate that perhaps it doesn't. Perhaps the brain is a radio and it receives consciousness from an external source. Transpersonal psychologists, among others. Is this a question that resonates with you, or one that you think is important, or not?
Yeah, on one level, I can't imagine, I can't think of any, I can't even get my head around the idea that consciousness cannot emerge from arise from the brain. So I can't even consider other possibilities just because I'm so embedded in sort of the idea that the brain does mediate behavior and the mind does, is mediated by the brain. But
the fact that you can monitor all these emotions and correlate them to brain activity, it could just be the radio receiving those things. And if all consciousness is also embodied and representative in the physical body, as some others believe, then the radio would be not just the brain itself, but the entire nervous system and even the organs.
Right, but then if I put my neurologist cap on, I've only seen disorders of consciousness with brain damage. I haven't ever seen a disorder of consciousness from a knee damage or heart damage or lung damage. So again, I can't again get my head around how it could be. So it's and one of the most common sort of symptoms that we see in patients with neurological damage is a change in their consciousness from one extreme where they're unconscious to other extremes where they're just unaware, that there's this disconnect between what they're aware of and what we know their brain is actually doing. And so patients that are clearly processing information at a pretty high level but are not aware that they're doing it.
Well, are you speaking about the unconscious versus the conscious now?
Yeah, I'm talking about sort of the ability to sort of implicitly process information at a fairly high level without explicitly being aware that you're doing that.
Well, Dr. Gazzaniga speaks about how they were astounded to find that the unconscious has access to all areas of the brain, and that he describes conscious awareness as something that happens sort of after the fact.
Yeah, I think
as
that's
an explanation
right.
almost of what's going on.
Yeah, I know, and that's sort of the newest idea that I'm struggling with as well, is that we've almost made decisions to act before we're aware that we've made a decision to act, and that's being borne out in experiment after experiment. And I see patients that make sort of decisions without being aware of why and make correct decisions without being able to explicitly state why they've made the correct decision. And clearly their unconscious mind has made the right choice, yet they can't say, they're not aware of it. It's kind of it's fascinating to try and figure that out.
Yes. So have the ad companies come knocking at you?
They actually have come knocking, not to me, but they have come knocking to several faculty at Berkeley about sort of a new way of thinking about sort of reading people's minds.
Yes.
For the purpose of advertising.
Yes.
And that's another sort of exciting thing that's come out of imaging. I think that you can read people's minds with brain imaging. It's phenomenal that you can look at brain activity and determine what picture what they've seen. And there's
what they're feeling,
what they're imagining.
And what they want.
And hopefully advertisers will translate to what they want. There can be still
don't tell them. Let there be some mystery.
Yeah, I think there will be a disconnect. Just because you're imagining doesn't mean that you want or will act in a certain way. I don't think we've been able to figure out how people are going to act. I think that's where the free will comes in, and that we haven't figured out yet, why people act in certain ways.
There's a book, The Mind and the Brain, Jeffrey M. Schwartz. Don't know if you're familiar with Dr. Schwartz. He dwells on plasticity a lot, and just the very idea that the amount of attention that a patient gives to whatever new function they're trying to restore with another part of the brain, the amount of attention and effort that they give affects the new neural patterns that develop. And if I'm not mistaken, I believe that he relates that to free will, and which is one of his interests in the book, and kind of a mind over matter almost, that you can mentally, the amount of mental attention you give has a real physical correlation.
Right. The kind of therapies that we've developed for improving frontal lobe function, a lot have to do with sort of increasing their attentional abilities, increasing their ability to sort of manage goals, to think about goals, to stop and relax and refocus when they're getting off track, how to enhance and attend to what's relevant and suppress what's irrelevant. And there's a lot of explicit a lot of the strategies that are taught, that if you can learn these strategies, it really does translate into improved frontal lobe function. But what's been surprising to us recently is that there's also, your brain has to be in a certain state to benefit from these strategies. What we've recently, and getting back to sort of the modularity idea, we've found that patients that these are brain damage patients who have more modular brains actually will benefit from therapy more than those who have lower, their modularity has been affected by sort of brain injury. It's suggesting that there is sort of a brain state that needs to be in place to sort of benefit from the therapies.
So some brain trauma affects key modules in ways that make it harder to rehabilitate.
Yeah, it doesn't affect, it's not that it affects a particular module, it affects the overall structure of the brain, sort of just puts noise into the whole network, and that areas are not connecting with other areas as well. And when the brain is in that sort of state, it doesn't seem to respond to therapy. And we can't tell beforehand. We can give them all types of neuropsychological testing, and we can't tell beforehand whose brains are less modular, more modular. They all look the same outwardly and to us, but when we image them, we see that there's differences. Now, the good news is that those with lower modularity, even though they didn't benefit from therapy, their brain got more modular after therapy. So now what we're trying to figure out is, okay, now have we sort of helped their network, and now we've put them in a state where if we do the therapy again, they'll benefit from it. So I think it's this combination of your brain has this state that has to be right, and you have to teach strategies to help boost its function. But this is the first time, at least in my career, that there's actually something where we think will actually help individuals with who've had brain damage from whatever the cause is.
And how big of a population is that?
Well, we're focusing on traumatic brain injury, which is one of the most common neurological illnesses in the country, and now with all the emphasis on sports injury, it's obviously much bigger than we thought.
Yes. I imagine that a lot of this will ultimately be applicable to post-traumatic stress syndrome, veterans coming back, things like that.
Yeah, and even illnesses that we kind of traditionally think of as psychiatric, obviously have a brain basis and are affecting the kind of systems that were that are affected in traumatic brain injury. So the same kind of therapy should apply to them. And and all of this is also complemented with pharmacological therapies, trying to manipulate neurotransmitters in the brain. And that's sort of an area of neuroscience that's been relatively neglected in trying to understand what the neurochemical basis is of behavior, and linking neurotransmitters like dopamine and acetylcholine and norepinephrine to sort of cognitive processes.
Is it fair to call the brain the most complicated structure in the known universe?
This is what I tell my students. I certainly tell them that when you put it up against the heart or the lungs, these other organs are just there to support the brain. So I'd say that's fair.
They're counting was it Dr. Gazzaniga that made the reference to the number of known atoms in the universe versus the neural connections in the brain, and the latter dwarfs the former.
Right. And even as we talk about networks and nodes of networks, it's certainly much more complicated, because now that we delve into it, we find that these networks are changing on a second by second scale, on the course of minutes, on the course of days. And so it starts to become sort of mind-boggling in a way to sort of understand how we're going to understand this network. It's one thing to say we've got 4 or 5 modules, but when they're reconfiguring over seconds, over minutes, and one node that was, acting in one way in one context and another way in another context, then the degrees of freedom starts rising, and it does start to make you wonder if we're gonna, if we are really gonna figure it out.
It also begs the question of free will, and I think Dr. Gazzaniga concludes that, and ultimately that question sort of vanishes when you understand the complexity of what's going on and the levels of emergence.
Yeah, I would agree. I think we sort of get the gist of it, just like we get the gist of what it means to understand the universe. But somehow we do believe there's fundamental properties about the system that we'll understand. But there's been, I think psychology, certainly psychological theory has really helped inform brain function, but it's certainly not, it doesn't always work out. The black boxes that are in models of psychology are not always mapped to the brain the way we may anticipate.
Well, are you formally in the psychology department, or is there a neurophysiology department?
There's a neuroscience institute at Berkeley that was formed about was formed when I arrived 12 years ago. I was the first faculty recruited to the Neuroscience Institute, and then I'm also in the Department of Psychology.
That's an amazing department, the Department of Psychology. Well, both, but you have Professor Gopnik and a lot of very good people doing great work.
Yeah, there's a breadth from social to developmental to clinical to cognitive. It covers all areas, and it definitely has become more brain-based, I would say, over the years. I'd say almost all the faculty in psychology, even if what they do is not study the brain, they're interested in trying to understand how the brain mediates the processes there.
Yeah, there's so much overlap, and
yeah,
it affects everything.
Right.
Have you read Dr. Gopnik's work?
I have, and I've heard her talk about it a lot, and I think that's another. I think developmental, the developmental neuroscience is sort of a very rapidly growing area because there's so much to learn about the brain by watching it develop. What we've discovered is that the way I study the other end of the spectrum at how it sort of changes with aging. And it's certainly not the case that the way the brain sort of changes with aging is not the flip side of sort of how the brain develops. There seems to be two different paths. And,
can you elaborate on that?
Well, it's just, I think the way, for example, the frontal lobes, one of the things we find with aging is that that frontal systems are the first systems to sort of change and deteriorate over the lifespan. And it's not simply sort of an undoing of what was the way it was sort of developed, the way sort of things come online in the frontal lobes are not sort of the way things deteriorate. But there are some commonalities. Like, for example, elderly patients, one part of the frontal lobe, like I said, is its ability to sort of tell the rest of the brain what's relevant and suppress out what's irrelevant. And with aging, it seems one part of that signal seems to be impaired. The signal that suppresses what's irrelevant seems to loses its function over time. So
everything seems relevant.
Everything seems relevant, but we let too much stuff.
Maybe that's wisdom.
That's probably the definition of wisdom. But we let too much too much information in. Elderly get too distracted by what's irrelevant. And so, and that is sort of true, and that's also true, and that is true in sort of development. You find sort of a similar thing that children are more able to sort of pay attention to what's relevant and sort of often get distracted. So and there are similarities.
So what, as we age, can we do to keep our faculties?
Yeah, well, I think some of the discovery that there is that not all attentional abilities are impaired, that there are actually that we can break this down into its components has actually helped in how we think about sort of therapy. So the kind of therapies that are now being developed for healthy elderly is about sort of learning how to filter out distraction and how knowing and taking advantage of that, the ability to focus on what's important is there and taking advantage of that.
And I imagine just keeping active, obviously, and everyone says to keep your hobbies, don't retire, get new hobbies.
Yeah, almost any way. It's thought that almost any way you can stimulate your brain is probably helpful, but knowing that there's specific, systems in the brain that are affected more than others, then we can target those systems. The other exciting thing is that just exercise has really shown to change brain function. There's been a number of studies now where just pure exercise, any way you want to do it, treadmill, walking, whatever, changes brain circuitry in elderly. And so that's an easy thing to do.
Excellent.
And so,
well, Dr. D'Esposito, thanks so much for coming and talking to us about cognitive neuroscience, and hope you come back and keep us informed on what's going on with your lab.
Thank you very much. I'd love to.
All right. Good talking to you.
Thank you.
And thank you for watching. Good night.